Imagine a machine so vast, so powerful, that it can recreate the conditions just moments after the universe began. This isn't science fiction, it's the Large Hadron Collider, or LHC for short. It is the largest and most powerful particle accelerator in the world, a monumental achievement of human curiosity and engineering. Built by the European Organization for Nuclear Research, known as CERN, it stands as a testament to our collective desire to understand the very fabric of reality. The LHC is our most sophisticated tool for peering into the subatomic world, a realm far too small to see with any conventional microscope, where the fundamental laws of nature are written. The LHC is not found in a gleaming laboratory on a hilltop. Instead, it is buried deep underground, about 100 meters beneath the surface. It sits in a massive circular tunnel that straddles the border between Switzerland and France, near the beautiful city of Geneva. This subterranean location was chosen for several important reasons. The Earth above provides natural shielding from cosmic rays and other background radiation that could interfere with the delicate experiments being conducted. Hiding it underground also minimizes the environmental impact on the stunning landscape above, allowing life to continue undisturbed while profound secrets of the cosmos are being explored right below. The sheer scale of the LHC is difficult to comprehend. The main ring, the circular tunnel that houses the accelerator, has a circumference of 27 kilometers. That's long enough to circle a small city. To walk the entire length of it would take you many hours. It is, without a doubt, the single largest machine ever constructed by humanity. Thousands of scientists, engineers and technicians from countries all over the globe collaborated for decades to design, build and operate this incredible scientific instrument. It is a truly international project, a shining example of what we can achieve when we work together towards a common goal. Within this enormous structure, scientists orchestrate one of the most extraordinary experiments ever conceived. The LHC is essentially a racetrack for the smallest known pieces of matter. These particles, called hadrons, are things like protons, which are found in the nucleus of every atom that makes up you, me, and everything we see around us. The goal is to accelerate these tiny particles to incredible speeds and then smash them into each other. By studying the debris from these high-energy collisions, we can learn about the fundamental particles and forces that govern the universe, uncovering the building blocks of everything that exists. So what actually happens inside this colossal underground ring? The process begins with something quite simple: a bottle of hydrogen gas. This is the source of the protons that the LHC accelerates. Scientists strip the electrons from the hydrogen atoms, leaving behind just the protons. These protons are then injected into a series of smaller accelerators that give them their first initial push, like a runner getting a good start before a long race. This chain of pre-accelerators gets the particles moving faster and faster, preparing them for their final journey into the main 27-kilometer ring, where the real magic happens. Once inside the main ring, the protons are guided by thousands of incredibly powerful superconducting magnets. There are over 9,000 of these magnets, and they are essential for keeping the particle beams on their circular path. To work properly, these magnets must be cooled to an astonishingly low temperature of -271.3 degrees Celsius. This is colder than outer space. This extreme cold allows the magnets to operate with extreme efficiency, creating immense magnetic fields that bend the path of the protons, steering them around the massive loop. It's an extraordinary feat of cryogenics and engineering on a scale that is simply mind-boggling. The protons travel in two separate beams, moving in opposite directions around the ring. These beams are not continuous streams. Instead, the protons are grouped into bunches. Each bunch contains about 100 billion protons, and there are thousands of these bunches racing around the tunnel at any given time. As they are accelerated, they gain more and more energy, eventually reaching a speed that is 99.9999991% the speed of light. At this velocity, a proton in the LHC will circle the entire 27-kilometer ring over 11,000 times every single second. Their journey is a frantic high-speed dance, choreographed by magnets and electric fields. The grand finale occurs at 4 specific points around the ring. At these locations, gigantic detectors have been built to observe the collisions. Here, the two beams of protons are steered by the magnets to cross paths, causing them to smash into one another. While the protons themselves are unimaginably small, the energy released in these collisions is immense. The detectors, which are multi-story structures packed with sophisticated electronics, act like giant digital cameras. They are designed to track and record every single particle that flies out from the point of impact, creating a snapshot of the subatomic world at the moment of creation. Why go to all this trouble to build such a machine and smash tiny particles together? The primary reason is to explore the fundamental nature of our universe. Physicists have a theory called the Standard Model, which is a wonderfully successful description of the elementary particles and the forces that govern them. It explains almost everything we see in our everyday lives. However, we know this model is incomplete. It doesn't explain mysteries like gravity, dark matter or dark energy, which together make up about 95% of the universe. The LHC is our best tool for pushing beyond the Standard Model. One of the most famous discoveries made at the LHC was the confirmation of the Higgs boson in 2012. The Higgs boson was the last missing piece of the Standard Model puzzle. For decades, it was only a theoretical idea, a particle associated with a universal energy field that gives other fundamental particles their mass. Without it, particles like electrons and quarks would be massless, zipping around at the speed of light, and atoms could never form. Finding the Higgs boson was a monumental triumph, confirming a key aspect of our understanding of the universe and earning a Nobel Prize for the physicists who first proposed its existence. Beyond the Standard Model, scientists at the LHC are hunting for clues to some of the biggest puzzles in cosmology. One of these is dark matter. We can see the gravitational effects of dark matter on galaxies, but we have never been able to detect it directly. It doesn't seem to interact with light, which is why we call it dark. One hope is that the high-energy collisions inside the LHC might produce new, exotic particles that could be candidates for dark matter. Discovering such a particle would revolutionize our understanding of the cosmos and what most of the universe is actually made of. Another profound question the LHC helps us investigate is the mystery of antimatter. The laws of physics suggest that the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a flash of energy. So if they were created equally, the universe should be empty. But it isn't. We are here, and everything we see is made of matter. The LHC allows scientists to create tiny amounts of antimatter and study it closely, searching for a subtle difference in its behavior that could explain why matter won the cosmic battle and why we exist at all. The work done at CERN might seem very abstract, dealing with concepts far removed from our daily lives. But the pursuit of this fundamental knowledge has always been a powerful driver of human progress. The technologies developed for the LHC have applications in many other fields. For example, the powerful magnets designed for the accelerator have helped improve MRI scanners in hospitals, leading to better medical diagnoses. The complex computing grid needed to handle the immense amount of data from the LHC has pushed the boundaries of data science and network technology, benefiting us all. Perhaps the most famous spin-off technology to come from CERN is something you are using right now, the World Wide Web. It was invented at CERN in 1989 by the British scientist Tim Berners-Lee. He created it as a way for the thousands of international scientists working on CERN projects to share information and data with each other quickly and easily. What started as a tool for particle physicists has since transformed our world, changing how we communicate, work, learn, and live. This is a brilliant example of how investing in pure, curiosity-driven science can lead to unexpected and world-changing innovations. Ultimately, the LHC is about more than just technology or discovering new particles. It speaks to something deep within us, our innate curiosity and our desire to understand our place in the universe. It is about asking the biggest questions we can imagine. Where did we come from? What are we made of? What is the fate of the cosmos? The LHC is a magnificent expression of the human spirit, a symbol of our relentless quest for knowledge. It reminds us that we are a species capable of looking beyond our immediate horizons and contemplating the grand, beautiful machinery of the cosmos. That is why the LHC is important for everyone, not just for scientists in lab coats. It represents a shared human adventure into the unknown. The discoveries made deep beneath the French-Swiss border belong to all of humanity. They enrich our culture, expand our perspective, and inspire the next generation of thinkers, explorers, and innovators. The Large Hadron Collider is more than just a machine. It is a beacon of hope and a promise that, as long as we remain curious, there will always be new wonders to discover just beyond the edge of what we know.